All right, this is the first, I guess, lesson of, I think I'll just do 2 videos for this unit because it's kind of all related. The first one is about precision and uncertainty. Now, these guys go together. And there's a third one that we discussed, and it's accuracy. Accuracy and precision, the way I always think about this is if somebody's, target shooting, for instance, and you shoot and you miss by 6 inches, you're not very accurate because you're trying to hit the bullseye. But if you shoot again and you miss by that same 6 inches and you can barely tell that there's 2 holes, you're very precise, but your accuracy's not there, right? So they're related very closely. By definition, precision is the smallest unit of measurement a tool can measure. And it also relates to how often that measurement can be reproduced. So if I think of a ruler that is marked in centimeters, so 0, 1, 2, 3, and so on, you could say that ruler has a precision of 1 centimeter. The uncertainty of that ruler is exactly half of whatever the precision is. So that same ruler that's marked in units of 1 centimeter, 0, 1, 2, 3, all the way up, you would say it has a precision of 1 centimeter and an uncertainty of half a centimeter. Okay? So we'll see in some examples where the precision could be different for different things. It could be decimal places. It could be... you look at your speedometer. What's the precision of your speedometer? Does it go up by 1 kilometer per hour, so that its precision is 1 kilometer per hour and it has some uncertainty? Or does it go up by 5? Is it the old needle type where it goes from 0 to 5 or 0 to 10? And then you could say how precise that is and how uncertain your speedometer is. Here's an example I've got here in an oven that only goes up by 5 degrees Fahrenheit. So you maybe want a 400 degree oven temperature, so you pump in 400, but you can't put in 399. It would go to 395, 400, 405, 410, and so on. So I hope that makes sense to you. So its precision is 5, and its uncertainty is 2.5. So what that actually means is the temperature may be 2.5 degrees higher or lower than what you actually think it is. So the closer it is to the actual temperature you want, the more accurate it would be. Okay? So if you wanted 400 degrees, you could say, okay, I'm going to set it 400 degrees Fahrenheit, like so. But it would be plus or minus 2.5 degrees Fahrenheit. So you might have a temperature that was 397.5. 397.5. You might be cooking your cake a little too much or too little. All the way up, it could be 402.5 degrees. Right? And there's lots of things where a recipe will say, depending on the how hot your oven or how cold your oven runs, it depends on the time. That's why lots of recipes will say it fluctuates, 10 to 12 minutes or 15 to 20 minutes, that kind of thing. Let's go on to another example. Here's 2 measurement tools. I did a speedometer, and then I've got a ruler, and I've got this guy here is actually a protractor here. So we'll see. So we'll just state the precision and uncertainty. So for the speedo here, and we'll write speedo. For the speedometer, the precision of this guy is, I can see it goes 0, 20, 40, 60. So those are going up in units of 20 kilometers per hour. So that would be how precise your speedometer is. And the uncertainty then would be half of that. So 10 kilometers per hour. So now you get a speeding ticket. Let's pretend you're speeding and you're going, here, I'll do a little bit different here. Let's say you're going 120, just right there. And the police officer comes to you and says, oh, you were going 120 kilometers an hour. And you using your essential math background, say, well, no, my speedometer has precision of 20 kilometers an hour, so the uncertainty on that, I could have possibly been going 110 kilometers per hour, right? And lower your ticket to 110. Now, I'm just kind of trying to show you the use of this, but that's the idea, right? Because you could have been going 10 kilometers an hour faster, depending on how off your speedometer is, right? Let's look at the protractor and the ruler. Let's just look at the protractor part, the round part. When I look at that, protractor, the precision of that guy, it looks like it's going up in 2, 0, 2, 4, 6, 8. Yeah, it's a little bit hard, but it's 2 degrees. Okay? The precision of that tool going this way is 2 degrees. Okay? So the uncertainty of that tool is 1 degree. So if you stated an answer, you measured something, you said that, oh, that's 8 degrees. You could never say 3 degrees because it goes up by 2's, right? 0, 2. You have to state that. Just like on your speedometer here, if I was going this fast, I can't say 30. As much as I want to say 30, I have to say either 20 or 40 with a plus or minus, right? That's the way these tools work. So I could say, oh, I'm going 8, or it's 8 degrees, or 38, or 58, or 128 degrees. But it would be plus or minus 1 for your uncertainty. Okay? So you got to be able to look at a measuring tool and know its precision. The ruler on the bottom here is in millimeters. So if you wanted to look at this ruler, now you'd have to flip the whole thing over. Okay? But the ruler here at the bottom is going up in 1 millimeter units. So you could say the precision of the ruler is 1 millimeter. So the uncertainty would be 0.5 millimeters. And you could convert those to centimeters if you needed to. Okay, so this goes with everything. This can be on any tool. You can go grab a tape measure right now, and maybe it measures 1/16 of an inch. So the precision would be 1/16 of an inch. Uncertainty would be 1/32. Okay, so it's always half. So let's go and do a couple examples. So express each measurement in the following. So your measurement plus or minus your uncertainty. So Barry measures a 2-meter piece of particle board. So my measurement is 2 meters. Using a tape measure that is marked in millimeter increments. So the precision of this tape measure is 1 millimeter. And the uncertainty would be 0.5 millimeter. Now that makes me think here. Oh yeah, we did that. So now the problem is if you notice, he measured it in meters and our uncertainty is in millimeters. So we've got to get them to be the same unit. So I'm going to say plus or minus, and using our old scale from grade 9, 10, 11, where you had your kilometers, hectos, your decas, your meters, right? Base unit of meters, deci, centi, milli. We're going from millimeters all the way over to meters. So 3 movements to the left. So plus or minus 0.0005 meters. So there is my measurement, right there, plus or minus my uncertainty, depending on the tool I use. Now that was a pretty hard one because we had to do some conversions, but this next one won't be so hard. A poultry farmer prepares 15 millimeters of antibiotics. So he's going to give his chickens some medicine, plus or minus. The syringe is marked in 1 millimeter increments. So again, we've got this whole 1 for precision, which isn't always the case. So 0.5, because half of my precision is my uncertainty. So 0.5 milliliters. So here's the safety factor in this. When you get medicine, when you get a doctor, a nurse, somebody, or a lab worker giving you a shot or something like that, and they drop antibiotics and say it's 15 mils, which is quite a bit, and that's how it's marked, as in 1 mil increments, that means you could be getting 15.5 milliliters, or you could be getting less than that, all the way to 14.5 milliliters. So you really want to use, the more precise the device, the more accurate it's going to be, okay, in this case. Okay, so here's another example. Speedometer on a car reads 35 kilometers an hour. So, okay, 35 kilometers per hour is my measurement, plus or minus. Now, how fast might it be going? Well, it's precise to 5 kilometers per hour. Its uncertainty would be 2.5 then, because it's got to be in between. So plus or minus 2.5 kilometers per hour. So that means you could be going 37.5 kilometers an hour and breaking the speed limit, or you might be going lower than the speed limit, 32.5. Okay? So that's just using that idea of measurement and uncertainty. Next one, state the precision and uncertainty each measurement if possible. So this is just more of the same. We're just stating the precision and uncertainty this time. A die maker makes a block. So here, this is a good example of decimal places. So you see here, there's 4 decimal places. We're in inches. So I can say the precision is 0.0001 inch. And its uncertainty would be half of that. So I just go to my calculator, divide by 2, and get that. Here, I'll erase this guy here. Oops. 5 inches. So you can have decimal places. That's how precise the device is. It might be a digital display or something like that. Even if it's digital, it still has uncertainty. Chef cooks potatoes for 58 minutes. We don't know any more other than it's in minutes. So I'd have to say my precision is 1 minute. So my uncertainty is half a minute or 30 seconds, right? Half a minute or 30 seconds. Let's put 30 seconds here. Okay, dairy farmer uses 8.2 kgs of feed. Again, you could say precision is just the number of decimal places. So 0.1 kg, that's the smallest unit. Uncertainty, divide that 0.1 by 2 and I get 0.05 kgs. Okay, perfect. Farmer needs 405 meters of pipe to install a watering system. Well, we don't know this specific tool, but going off of what he's given us for a measurement, we can assume that his precision is 1 meter and his uncertainty is 0.5 meters. So there's the precision and uncertainty, if it's possible to tell. Okay, we're just going based on the measurements. Okay, last one. This is kind of a neat one here because there's 3 measurements. There's 9.4 kilometers, 0.5 kilometers, and 0.3 kilometers. So this is what happens when you get multiple measurements. So this might be 3 things you've weighed and you're going to add it up. Or you've taken 3 measurements of boards and you're going to put those boards all together. In this case, a truck driver estimates his distance from a landfill to a job site to be 9.4 kilometers. He adds a half kilometer for travel inside the job, 0.3 at the land site. What's the combined distance? Well, you take your measurements, 9.4, 0.5, and 0.3. You can add those up pretty easy here. We got 9.4, 9.9, 10.2 kilometers. So there's the actual measurements. Now the uncertainties. If we look at our first measurement, we can see that the precision of the first guy is 0.1 kilometer. And in fact, we can see that's the precision of all 3, right? Because they all have 1 decimal. So that means the uncertainty is 0.05 kilometers for each measurement. So now every time you make a measurement, you've got uncertainty. Kilometers, kilometers, and kilometers. So it's plus or minus. We have to add all those up, and I get 0.15 kilometers. So this truck driver may have driven 10.35 kilometers over this whole trip, or he may end up only driving 10.05 kilometers. But the idea is that he measured 3 different things. Therefore, he has 3 different uncertainties in his issue. So, not the craziest idea, okay, of all time, but as you look at more and more things that have actual measurements on them, you'll hopefully look at them as how precise are they, right? Does it make sense to use your arm to measure how long something is? Is that precise enough? Or would you want to have something with more smaller digits on it rather than your shoulder to your fingertips, that idea of precision.